In this video, we're going to talk about quadratic programming. All right, so let's start with what is the basic structure of quadratic programming. And the way that I like to think about it is we're going to start off with the linear program. So, maybe something like this. And we're going to add on a quadratic elements of the cost functions and also quadratic elements of the constraint equations. So maybe we have something like 1/2 x transpose q times x. And on the constraint side, we might add in 1/2 x transpose p times x, and it's still less than or equal to b. And so if we want to have a linear formulation, then we would just set q is equal to 0 and p is equal to 0. Now these are the zero matrices, right? So they have to sort of match up with the dimensions of whatever x is. All right. Now, we have to have certain properties regarding p and q in order for Cplex and virtually all optimization solvers to be able to solve them. And in particular, we require that p and q be positive semi-definite. So we write that by saying q is greater than or equal to 0 and p is greater than or equal to 0. Now when we say q and p are greater than or equal to 0, and actually sometimes you'll see it, it's sort of written like a curly greater than or equal to. When we write this, we're not talking about the values inside of the matrix P or Q. In fact, what we're talking about are the eigenvalues. So let's say we solve for the eigenvalues of Q. What we'd require is that each of the lambda i's, the eigenvalues, are greater than 0, greater than or equal to 0. And likewise for the eigenvalues of P, the lambdas are greater than or equal to 0. All right, so why does this matter? Well, for starters, let's study sort of this idea of Q. All right, if Q is positive semi-definite, then what this does is this essentially implies that our objective function is convex. Okay, so again, we can think of that if Q is positive semi-definite, we're going to have a bowl. All right, so why is this bowl useful? Well, the way most optimization solvers work with quadratic programs, they basically start off at an initial point and they keep following the derivative. All right, and so if you have this bowl shape, they can just keep going down the derivative, and it's really, really nice. Now, let's say Q was not positive semi-definite. Right? And you had something like this. In this case, it would be negative semi-definite, convex down, or concave. We can't really minimize this function because let's say we started here, right? Depending on where we start, we're either going to move down to this optimal point, or maybe we'll move down to this optimal point. And so the solvers can't guarantee the optimality of the solution. All right. And so for that reason, Cplex and most optimization algorithms are sort of founded on this premise that they're working with objective functions that are at the very least are bowl-shaped. Okay. So we require that Q is a convex function, or positive semi-definite, which, if that's the case, this function here is convex. Okay. So our objective function follows this bowl shape. All right, so this brings us to the constraint equation. Now, we're going to have similar requirements on P. All right, so why is this? Well, for starters, our constraint sets have to be convex. Now, we've talked about convex functions. There is also the same idea of a convex set. All right. All right. So the general rule about a convex set, and I'm going to draw this out, and then I'll write the mathy equivalent, is that if we take any 2 points inside the set and we draw a line connecting them, then every point on that line is also contained in the set. Now let's contrast that with a non-convex set. Okay, so let's say I had a set that looked like this. All right. I could certainly select 2 points. I can try to connect them, but what we see is some points on the line that connect them are outside of the set. So we could sort of write this quickly by saying a set S is convex if for all x and y in the set, then alpha times x plus 1 minus alpha times y is also in the set for all alpha between 0 and 1. Okay? And that's just basically the math equivalent of what I just described, right? You pick any 2 points, you draw a line connecting them, that line has to be within the set. Okay, so what does this have to do with positive semi-definite matrices when we have a quadratic constraint here? Okay? Well, the reason is, if we look at this constraint, and we can actually build this up. So let's say when we just had AX is less than or equal to B. What did these constraints look like typically? Well, they were polyhedra. Okay, so, it could be an n-dimensional shape. It doesn't really matter, right? But basically we'd have a lot of hyperplanes that would sort of create this polyhedra shape. Now, the neat thing about these polyhedra shape, any set of linear constraints are also convex. So any feasible linear constraints that can be represented by AX is less than or equal to B is a convex set. Okay. Even if this constraint was not feasible, it'd still be convex, all right? Because the little trick here is, let's say S was equal to the null set, then if we are to pick any 2 points inside of S, well, that would mean X is equal to the null value, Y is equal to the null value, and certainly any linear combination of null is also part of the null value. But for our purposes, we're going to just assume that AX is less than or equal to B. This constraint defines some sort of like polyhedra in a hyperdimensional space. All right, so now let's think about the simplest quadratic equation that we could write. Okay, so maybe one quadratic equation I could write is x1 squared plus x2 squared is less than or equal to 5. Okay. And so effectively what that does is draw a circle in 2-dimensional space, and our feasible space is everything inside. Okay. Now certainly if we take 2 points and we connect them, then everything on that line is inside the circular set. Now, all positive semi-definite matrices, so any quadratic that we can write as X transpose QX, where Q, again, is positive semi-definite, and I should put set, is convex. Okay. All right. So, really what Q does, all right, so the Q matrix in this case is actually pretty simple. The Q matrix here would be X transpose times the identity matrix times X is less than or equal to 5. Okay, that's not too bad. But we could make more complicated Qs here. Okay. And really all that these complicated Qs do is that they sort of morph the shape of this set. All right. So what they do is they transform them into ellipsoids. All right. So if we have some other sort of Q matrix, it might do something like make an ellipsoid like that. And certainly we could imagine this in three-dimensional space. Okay. So this is sort of an ellipsoid, might look like a football. And again, if we take any 2 points and inside of that ellipsoid and we connect them, that line is still within the ellipsoid. Okay. Now, if Q is not convex, then we don't have this property anymore. All right. So maybe later on in the semester at the very end, we'll go into some of the more mathy stuff. But for now, I sort of just want to teach you the concepts so that we can program quadratic programs, okay? All right. So these are the two important features that we require from the matrix Q and the matrix P, is that they have to be positive semi-definite so that we can ensure that our cost function is convex, so it's a bowl, so we can minimize it. And we require that P is positive semi-definite, and that will ensure that our set is also convex. Now it ends up that if we have a combination of a quadratic with a convex, then that's also convex, okay? So any constraint set so anything that can be written as AX plus 1/2 X transpose Q times X is less than or equal to B. Oops. Where Q is positive semi-definite is convex, is a convex set, sorry. Right. And so this is sort of generalized so that if we wanted to just purely be convex or quadratic, then we could set A to be equal to 0. Or if we wanted to devolve to a linear constraint, then we would set Q to be equal to the 0 matrix, and we'd just be left with linear constraints. Okay. All right, so let's look at some problems and sort of see how this works out, and I'll sort of work out some of the mathematics of what's going on. All right. Algebraic, so we'll do a couple examples. So, and again, these are called quadratic programs. Okay, so QP, quadratic program. Okay. So let's say we had the following optimization again. So we're going to minimize C transpose X plus 1/2 X transpose Q times X. And I'm going to fill in what Q is later on and what C is. And we'll do it subject to some constraints. And well, maybe we can have two sets of constraints. So we'll have AX is less than or equal to B. And perhaps we have something like fx plus 1/2 x transpose p times x is less than or equal to d. Okay, so I'm just going to fill in a few values so that we can actually solve this problem. And we're going to, again, have some requirements on the convexity of our cost function and of our constraints. All right. So for C, I'm going to select the values 5, 3, and -1. All right. For Q, we'll have 2, -1, 0, -1, 2, -1, and 0, -1, 2. All right. For AX less than or equal to B, why don't we set A to be a matrix 1, 1, 1, and then we'll do 2, -1, -2, and B will be 5 and -5. All right. At this stage, the only ones that's missing are F and P. And just for simplicity, because it really doesn't change how we formulate this, I'm going to just pretend F is 0. Make my life a little bit easier. And for P, we'll use the following matrix. 1, 1, 0, 1, 1, 0, and then 1, 1, 2. Okay, so one of the first things that we're going to check is whether Q and P are quadratic equations, or are positive semi-definite. So I actually probably already did this, so I'll just do it again. So the first thing is we can type in what Q is, and I'm loading up Octave. So if you have MATLAB, use MATLAB. If you have access to Octave, then go ahead and install Octave. And I'm just typing in what the Q matrix is. For those of you who haven't used MATLAB or Octave before, you just type in the name of the variable, you say it's equal to something, and you put up square brackets, and then for each row you put in a semicolon. Okay, so there goes Q. I can do the same thing for P, so I'll sort of, again, P equals, square brackets, 1, 1, 0, semicolon, 1, 1, 0, semicolon, 1, 1, 2. Okay, so the first thing we want to check are the eigenvalues for Q and for P. And what you can see is if we look at the eigenvalues, all these values are greater than 0. So that tells us, in fact, that Q is convex, or positive semi-definite. All right, and our objective function will be convex. Okay. In terms of P, we can take the eigenvalue of that. And again, these guys are all positive, non-negative, right? So the 0, 2, 2. So we're positive semi-definite. Okay. Now, when you have an objective function like this, the important part is linear equations are both convex and concave. All right, so that might be a little bit weird, but let's think about it. So convex, we say that the double derivative, so if you take the double derivative of the function, right, f of x, then that is typically less than 0, or sorry, greater than 0, and that would be convex. Right, if we took the double derivative of the function and we got less than 0, it'd be concave. Okay, but you see I have less than or equal to and greater than or equal to. And what happens with a linear equation, if we take the derivative, let's say we take the derivative dx, double derivative of c times x, all right, that just gives us 0. Okay, so that is both greater than or equal to 0 and less than or equal to 0. So that's why when we look at our objective function, C transpose X is actually convex and concave, but we can sort of take it in the most general sense. So the C transpose X is convex, and because the eigenvalues of Q are greater than 0, those are also convex. The same thing is true, again, for these linear constraints. They end up being convex. And if we were to have this case, we have a convex and a convex. And the one rule is if you add a convex function and a convex function, you still have a convex function. So these are kind of neat little properties. We're not going to go too much into them because we're just going to mostly focus on the application of quadratic programming. All right. So again, if we use these matrices, then we have a quadratic program that is actually solvable because our objective function is convex and our constraints are all convex. All right. Now, it's kind of hard to see the relationship between this guy here, which I've told you is quadratic. Okay, so for those of you who might need your linear algebra brushed off, we can sort of figure out why this is a quadratic equation. So what I'm going to do is I'm actually going to calculate x transpose q times x, and we'll sort of work out what that is actually equal to. Okay, so let's do that. And so we'll plug in all the values. So x transpose is just x1, x2, x3. Right, our Q matrix, 2, -1, 0, -1, 2, -1, 0, -1, 2. All right, and then we're going to multiply that times x. Okay, so this is just an example where we have a 3 by 3 matrix, which means we have 3 decision variables. So let's go through and do this multiplication. So again, we're doing row times column, row times column, row times column when we multiply these first two parts. So if we do that, we end up with 2x1 minus x2. All right. Our next element is going to be minus x1 plus 2x2 minus x3. Lastly, we have minus x2 plus 2x3. Okay. Now that's going to get multiplied times x1, x2, x3. Equal. All right. So let's go ahead and now do that multiplication. So at this stage, this multiplication is going to result in a scalar. So we get 2x1 squared minus x1, x2 minus x1, x2 plus 2x2 squared minus x2, x3 minus x2, x3 and plus 2x3 squared. Okay, so we can do a little bit of simplification here, and we end up with 2x1 squared minus 2x1 x2 plus 2x2 squared minus 2x2 x3 plus 2x3 squared. Alrighty. So if you want to, and in fact, what we're going to have to do in Cplex is actually write it in this algebraic form. Okay. And so a lot of times, you know, depending on what field you're working in, the Q matrix is pretty obvious, right? Other times it's not. So depending on how you sort of program your optimizations, whether you're using MATLAB or Python, sometimes you'll actually just feed in the Q matrix. Other times, like in Cplex, you'll feed in this equation here. Similarly, we can do the same sort of thing with the P matrix. All right, so we might want to calculate what X transpose P times X is equal to. If you end up doing this, you end up with x1 squared plus 2x1 x2 plus x1 x3 plus x2 squared plus x2 x3 plus 2x3 squared. And I never gave you guys a d here, but we'll just pretend, I don't know, d is equal to 5. Why not? Okay. So we're going to say all this will end up being less than 5. Okay, so let's sort of put this together. So again, one form was the matrix form where I gave you the matrices, but let's sort of write this all out in as the full optimization, and then we'll program it in Cplex. So first we'll go ahead and do the linear part. So we end up with 5x1 plus 3x2 minus x3. At this point we have the quadratic part, so we're going to have plus 1/2 2x1 squared minus x1 x2 plus 2x2 squared minus 2x2 x3 plus 2x3 squared. So hopefully I wrote that in all correctly. Now you might notice that one thing I've done is I have this 1/2 here for both of these quadratics. And it's actually kind of worth explaining where this comes from. The reason is because it makes the math a lot easier. So I'm going to sort of scroll down here. So let's say I wanted to take the derivative of 1/2 x squared. Right? If I was taking that derivative, I would just say, oh, that's equal to 2x. All right? And that's why this 1/2 is sort of included. It makes the math easy when you're calculating derivatives. So why do we care about derivatives? Well, if you remember when we were talking about how Cplex sort of works in sort of a vague and abstract way, I mentioned to you that we sort of pick a point and we start following the derivative or the gradient moving downward. And so in order to calculate this df dx, right, the direction of which way the derivative is going negative, right, so which way you go down, you want to make the derivative easier to calculate. And so historically what we've always done in optimization is we usually put a 1/2 before these terms because they make the derivatives a little bit easier. When you're working with matrices and you take the derivative, so actually we'll call it the gradient. So let's say we're taking the gradient of this guy. We end up with X transpose Q. Okay. So yeah. Okay. And again, that's the same idea. What happens is this is like an x squared, but it's not, right? And when you take the derivative, it ends up canceling out this 1/2. And that's why we don't see that constant. Okie dokie. Okay, so we got our cost constraint. All right. The next thing that we're going to do is write our constraint equations. And so I think I gave 2, so you can see the A matrix there. So we have x1 plus x2 plus x3 is less than or equal to 5. And I'm getting that from the A matrix here and the B matrix there. Next we have 2x1 minus x2 minus 2x3 is greater than or equal to -5. And lastly, we have this quadratic constraint, which we can write as 1/2 2x1 squared minus 2x1 x2 plus 2x2 squared minus 2x2 x3 plus 2x3 squared. And we said all that is going to be less than or equal to d, which we said was 5. Okay, so now we have sort of written from matrix form to algebraic form our optimization. So let's go ahead and actually type this in to Cplex. Okay. So I've gone ahead and sort of started the problem, but I'll actually better just go ahead and erase this because I was playing around with it. And as a good start, I'm going to just write out the linear components, right? So we've defined our variables x1, x2, x3. Here we have the standard C transpose x, all right? And now I'm going to write in the constraint equations that we have. And so I'm going to sort of peek back in. So we have x1 plus x2 plus x3 is less than or equal to 5. All right, so that was one of the linear constraints. 2, -1. All right, so 2 times x1 minus x2 minus 2 times x3. And what did we say? Oh, wrong one. That was going to be greater than -5. Okay. Okay. Now at this point, why don't we go ahead and solve it? And what we're going to see is we're actually not going to have a feasible solution. So I've gone ahead and typed this in as, my first QP. I set configuration 3 with my first QP, and I set that to the default. Okay. Sometimes I made this mistake where I had configuration 1 as the default, and I kept pressing play to solve it, and it kept solving my furniture problem. And I wasn't solving the actual problem that I was working on. So make sure you go ahead and set this as the default. And then from there, you can press play. Okay. So at this stage, I'm actually not going to get a solution. All right. So you see here, no value, no value, no value. Everything about this is sort of saying that there's no solution. Okay. Okay, so this problem is not feasible. You can do that thing where it prints out. Let's see if I have the code. I think I did that in a prior problem. Oh, I didn't. Okay. Well, either way, this guy's not solving. But what we can do is we can start adding in our quadratic cost function and our quadratic constraint. So right now, this is just the linear version. Okay, so if we want to sort of keep track of what we've programmed in, we've programmed in this part of the cost as well as this part. And so the question is, how do we program in the quadratic? All right, so I'm going to post the Cplex manual here. And there's actually, supposedly this tells you how to use the optimization studio. But I'm going to be honest, it's not actually the best documentation. It's quite a bit confusing. And the reason for that is it actually tells you how to program using the interactive optimizer, the studio the Optimization Studio, but it also gives directions on how to do it in C++, Java, C, and it might even have Python, which isn't really helpful if we're trying to do this in the Optimization Studio, which I don't get while they do this. It's not clear. So the question is, how do we program in these quadratic programs? All right. So if you'd, and again, they sort of walk, I'll post this online, but they sort of walk you through, again, they talk about the bowl shapes that I talk about and that we've mentioned. So how do we enter in these quadratics? Okay. And it's not quite clear. So before, when I was using the Cplex Interactive Optimizer, that's the one where you could do the sensitivity analysis, I used to type it in this way. But for some reason that doesn't work with Optimization Studio. So I'm giving you fair warning. And so what I suspect is they actually let you enter it in kind of like how you might type it in normally. And I don't even think you have to do the 1/2. So let's sort of check on these different options. Okay, so again, they don't really tell you how to program this in, which is really disappointing. Alrighty, so flipping over here, what I'm going to do is I'm going to try to typing in, so the optimization, in the way that I would think Cplex would normally do it. So usually Cplex, you know, in the old different versions, I would write square brackets and then do the constraints. And well, I'll do it and I'll show that it doesn't work, right? So this is sort of problematic. So let me remember what the cost equation was. Okay, I think I got that. Okay, so we have 2 times x1 up 2 minus 2 times x1 times x2 plus 2 times x2 up 2 minus 2 times x2 times x3 plus 2 times x3 up 2. Okay, so right now all I've done is enter in the quadratic and I put it in square brackets. And that's how I used to do it using the interactive optimizer. But here you can see we're in the Optimization Studio and we use the optimization programming language, OPL, okay, which is a bit different. And we see that an error is coming up. So it doesn't really understand what's going on. And so my first thought was, oh, maybe it doesn't like these square brackets anymore. Let's try parentheses. Okay. And all of a sudden we see that error go away. So when you type in your quadratic, we're going to start by just trying in these parentheses. All right. And let's go ahead and see if we actually get a solution. It's running, which is promising. And bam, there we go. We have a value of -5, -5, and -2. All right. All of a sudden, our problem became feasible. What that meant is without this quadratic, so before, when we had that, the problem was infeasible because it was unbounded. All right. It could be as negative as it wanted. But the moment we added this quadratic, it became bowl-shaped. And so it's sort of limited on how negative it could get. Alrighty, so let's do another test. This is something I actually don't know. Let's see if we actually need this divide by 2. Alright, so it didn't seem to throw an error sign here. Ooh. And we still got a solution. Now, the solution's going to change because the relative importance between the quadratic and the linear part has changed. All right, so now let's check one more thing, if we even need these parentheses. All right, so I think this programming language the OPL is actually a little bit more advanced than other versions of Cplex in that we can just write the quadratic. So that's good news. Okay, so if you want, just go ahead and write the quadratic as you would normally do that. Okay, so just to represent the same problem, I'm going to go ahead and divide everything by 2, which is great that Cplex can handle this. So again, this gives us good news. So if we wanted to, we could sort of write it the traditional way where you put all the quadratic terms together, right? Alternatively, if you wanted, you could divide by 2 everything, right? So I could do that, get rid of the 2 there, get rid of the 2 there, get rid of the 2 there, get rid of the 2, and get rid of the 2, and have no parentheses. Okay, so if I were to, I'm going to comment this out. These should give me the same answer. So let's sort of check this. All right, so I'm going to run this. -5, -5, -2. All right, let's compare that to what we had before. All right, where we had the parentheses and divided by 2. So same answer. Okay, so that's kind of nice. Cplex has at least advanced in some ways. So you can just type in your quadratic equation here. Now this gives us hope that we can do the same thing for the constrained equations. All right, so I'm going to go ahead and test this out. So again, if you remember, we had 1/2 times this big long constraint, and that's going to be less than or equal to 5. Okay. Sorry, I'm just checking to make sure that I'm going to be typing in the right thing. Oops. Oh, so I definitely copied it down wrong because I should have x1 squared. Oh, did I copy down the wrong equation? Oh, no, it's because I copied down the wrong equation. Sorry, so this is incorrect. All right. So it should have been this guy here. All right, so it should be 1/2 x1 squared plus 2x1 x2 plus x1 x3 plus x2 squared plus x2 x3 plus 2x3 squared. Okay, there we go. So all that stuff has to be less than or equal to 5. All right, so we're just going to go ahead and try to type that in. All right. So x1 up 2. Oh, now I'm confusing myself. Just x1 up 2, 2x1, yeah, okay. Plus 2 times x1 times x2 plus x1 times x3 plus x2 up 2 All right, and this is all going to be less than or equal to 5, and we'll finish it off with a semicolon. Okay, so hopefully this is still a feasible problem. All right, we got no errors. Ooh, no, we did get 2 errors. What did it not like? Processing failed. Oh, it's not convex. Ooh, did I type this in wrong? I must have calculated something wrong. So let's sort of check. So this is actually kind of useful because when we tried to solve it, you can see the error, Q1 is not convex. So it's saying that this constraint is not convex. And let's just quad constraint. So I'm going to put a colon and name it. And so again, let's see if it comes up with the same error. So it's going to run it or try to solve it. And we're going to just make sure Q1, this error that it's referencing. Yeah, so it says quad constraint is not convex. All right, so I think I did something wrong with my math. So this is kind of useful to know that at least it can catch it. Okay, so let's sort of check what I did wrong. Did I copy something down wrong, or did I type it in wrong? Okay, so I'm going to check this again. So x1, 2x1, x2. This should be x3 for starters. x2 squared, x2, x3, 2x3. Okay, so now let's give this a shot. Oh, and there you go. So now what we can see is that we are able to solve this problem. It gave us the x1, x2, x3 constraints in order to do so. Okay, so what's the end message? Which is when you're using the Optimization Studio, you can pretty much type in your quadratic equation as you would like. And you can have linear components and quadratic components. Similarly, on the constraint side, you can just type in the quadratic. So, in fact, what we could have done is we could have multiplied both sides by 2, so we can get rid of this times 1/2, and we can say it's less than or equal to 10. And so we should get the same value of 2, 1, and 1/4, approximately. Let's go and run that. And sure enough, we got the same thing. Okay, so that's really nice. You can just type it in. Before, you couldn't do that. Now, the issue that I have is that this user manual, I think I told you, it gives you instructions for everything except the tool that we're using, which I don't really understand why. So you can see here it looks like they're using the Optimization Studio, kind of, but not really. But they never actually have a real example. And so I think this is one of the biggest challenges with Cplex when you're using the Optimization Studio. But if you ever want help with the Optimization Studio, your best bet is to actually do a search in Google for what you're trying to do, and then OPL. So that is the optimization programming language that we use in Optimization Studio. Okay, so if you ever need help, just do OPL, Cplex Quadratic, and hopefully you'll find what you're needing. Again, I think it's very unfortunate. IBM this past year got rid of their help forums, and they also changed the format at which their manuals are listed. Okay, but here you can see they have an example of a quadratic program and a quadratic constraint. The neat part is they actually, like I said, they do this traditional thing where they put a 1/2 in front, and then they put the quadratic part in parentheses. So, but what we've learned is you actually don't need to do that in order to solve the program. Okay, so that's sort of a quick lesson on how do we implement quadratic programs in Cplex. Uh-oh, where's